Second talk is going to be given by Daniel Sussman, and he's talking about bias variance trade-offs in joint spectral embeddings. So thank you very much, Daniel.
Thank you. Yeah, and thanks to the IMA and everyone there for organizing this. So this is some kind of recent work with a student of mine, Ben Draves, so he's a PhD student at Boston University, and so a lot of the credit for this, I will say, goes to him and some of the figures and stuff like that as well. I know with Zoom it's a little bit difficult, but if you do have questions, please interrupt me, I think I'll try to adapt to that. So yeah, please do. Okay, so the kind of data structure that we're going to focus on in this talk is multiplex networks. So these are networks that can basically encode different kind of relationships. So for example, here we have 5 different networks. Each of these networks is on the same set of people. So each node, the positions of the nodes are the same across each of these figures, and each link in the different figures corresponds to a different type of relationship. So for example, this is who eats lunch with who relationship, and then we have who's Facebook friends with who, a co-author relationship, and then leisure, work. Okay, so each of these kind of encodes maybe a different part of people's social network and how they're interacting, and presumably kind of encode different aspects of each person's personality and how they're interacting across these networks. So applications for multiplex networks kind of are all over. A really good kind of overview of multiplex networks is this Cavella paper with Mason Porter from 2014. Talks about lots of different kinds of multi-layer networks. But there's applications in international trade, transportation systems, neuroscience. Anytime you're collecting multiple modalities of data, and then also additionally kind of when you're dealing with time series of networks or something like that, where you want to be able to understand how these networks are evolving over time, what's in common and what is changing. Okay, so as a kind of toy example of what we're going to do, and after the next couple of slides, you can probably you'll probably get the main point of the talk, but I'll go into more details after this. But so on the left hand side, I'm showing you 3 networks, and these 3 networks, these are all simulated networks. They're from a stochastic block model. So if you're not familiar with stochastic block model, basically, there's red nodes here and there's blue nodes, and the probability of adjacencies among the blue nodes is 1 probability. The probability of adjacencies between the blue and the red is another, and then same with among the red. So, so in this top network, we have, the red and the blue, and it happens that the nodes of the same color are tending to connect to each other more frequently than they are to other colors. Okay, and that's pretty clear even on this left-hand side. In the middle, same idea, but the structure isn't as strong. So there's a little bit less community structure, and it's a little harder to detect and do the community detection. And then in the bottom, we have something where basically there's no structure at all. So each edge has the same probability of appearing, and you don't see any there's no way that you could distinguish between the red and the blue in this network. Okay, so we're going to use an embedding approach. So the embedding the kind of that we're going to think about is called the adjacency spectral embedding, which is essentially, if you're familiar with kind of spectral clustering and stuff like this, it's a variation on this that is a little more motivated by some modeling and things like that. But the basic idea is that I take the adjacency matrix, I look at the largest, in this case, 2 eigenvalues and the corresponding eigenvectors. And here I'm plotting the eigenvectors scaled by the square root of the eigenvalues. So the x-axis represents the first eigenvalue, the y-axis is the second, and each point is basically a row of that 2-column matrix. Okay, and so here I'm showing you doing 3 separate adjacency spectral embeddings. So I'm doing an embedding of this first network, and you can see that when I do this, I get a pretty clear view that there's a difference between these 2, red and the blue, right? In fact, they look like they're linearly separable, right? So I could probably figure out from this that there are 2 clusters. I might not do a perfect job, but I would do okay. From the other 2, though, right, this second one does have some community structure. This last one does not. But from a embedding perspective, there's not much difference between them, right? It's hard to tell whether, you know, the second one has any community structure. Okay, so we can, you know, so we do this, and we can, if we want to kind of study these together, we could try to combine these 3 embeddings and do statistical inference on those. The other approach, which I'm going to focus on, is going to be a joint spectral embedding. So a joint spectral embedding, what it does is we're going to combine the information from the different networks, and then we're going to kind of simultaneously embed all of them, and we're going to get we're still going to get separate embeddings for each network. Okay, so each of these now is representing kind of the same network, the same corresponding network, but they're going through this joint process. So now at this point, right, you can see that the first graph, still we see pretty clear distinction, and then in the second graph, essentially what's happening is the joint embedding is kind of taking into account the fact that, you know, there is actually shared structure between the first and the second, and so it makes it more clearly able, you're more clearly able to from this embedding see that actually, yes, there are 2 groups in this left network. And then for the last one, you actually see that even though there is no structure, the fact that we are jointly embedding kind of biases the embedding in a way that it starts to pull apart the red and the blue nodes, so that you can so that you see community structure where there isn't any. Okay. Okay, so that's kind of so the idea here is, right, that by jointly embedding, we can kind of borrow strength between the different networks and find common structure. And it does introduce bias, but often this bias is something that we want. Okay, in the sense that by combining the different networks, we are kind of lowering the variance, lowering the noise in our embeddings, and we're able to do a better job on our final inference task, whatever that is. So the bias usually often is something that we don't that doesn't bother us too much. So I want to kind of go a little bit into the model that this is based off of, and introduce some of the techniques and the theory. So the model that this is based off of, I was showing you stochastic block models. Stochastic block models are a example of a latent position graph, and the one that we're going to look at is called a random dot product graph. The key thing here is that if we look at pairs of nodes, okay, for each node, we're going to associate with it a latent position XU, okay? So XU represents the latent position associated with XU. And then in a random dot product graph, we have that the UV entry of the adjacency matrix conditional on the latent positions has a Bernoulli distribution with mean given by, or success probability given by the inner product between the two latent positions, okay? So it's, pretty straightforward, bilinear function here to get from the latent positions to the probabilities. And if we take our latent positions and stack them up into an n by d matrix, so n is the number of rows and d is the latent position dimension, then it turns out that A, conditional on that entire matrix X, that the matrix A is a Bernoulli matrix with mean given by X transpose, okay? All right. This imposes a few different conditions. So for example, it imposes that the rank of the expectation of A is at most D. Also, in this case, the expectation of A, at least up to some diagonal, some issues with the diagonal, is PSD, positive semi-definite. You can have indefinite matrices and things like that. Like I said, this is an example of a more general class of latent position models. And you can incorporate sparsity in various ways. I'm not going to talk about sparsity, but it is an important problem when you're thinking about these large network situations. Okay, so as an illustration, right, so on the left-hand side, I'm showing you some latent positions. There are, again, blue points and red points, but in this case, kind of the blue points are, mostly in the upper left, and the red points are mostly in the bottom right, but there's noise in that structure, right? So there are kind of two communities, but in this case, there's a little bit of mixing between the communities, right? They're not all in the same, at a single location. If we had a stochastic block model, there would we'd only see kind of 2 points, and all the nodes would be at exactly those 2 points. And if we then take the inner product, we get our low rank, our rank 2 probability matrix. And if then we take our if then we look at the adjacency matrix, it's going to be a noisy version of this probability matrix. Okay. In social networks, we can do things like imagine that each direction represents an interest in a different topic. So music, math, sports, etc., right? And then the magnitude of the latent position represents some notion of popularity, okay? There are some issues with identifiability. I will, hopefully when needed, talk about them, but they are mostly due to the fact that inner products are invariant under orthogonal transformations. So any inference we're going to do, any estimation we're going to do is going to be up to that equivalence class. So we do have to kind of keep that in mind. So the main question, right, is if I got to see the latent positions, right, I have kind of all of the tools of statistics, machine learning, multivariate analysis, right, that I can throw at it, right? There's a whole, right, points in Euclidean space, we have a lot of things that we can do with them, and we a lot of tools available. If I have this right-hand side, right, there are, of course, many tools, and many people at this conference are developing tools to deal with this. But one approach would be to say, okay, if we could represent it as a kind of Euclidean structure, then that would allow us to additionally employ all of those tools from multivariate statistics, etc. Okay. So the goal, to some extent, is to estimate these latent positions based off of observing this adjacency matrix, right? So we're going to observe the adjacency matrix, and we're not going to observe the latent positions, and we want to estimate those. So it turns out that if you take, if UA is the largest D, or sorry, SA has the largest D eigenvalues of A, and UA the corresponding eigenvectors in an n by D matrix, then and SA is diagonal, then you end up with, if you take X hat equal to UA times SA to the 1/2, then that serves as a pretty good estimate. And again, the left-hand side is showing the original latent positions X. The middle here is showing our estimated latent positions based off of observing just A. I did kind of cheat a little bit in that I did take into account that orthogonal transformation. So I did kind of, for identifiability purposes for visualization, line these two up so that you could kind of better compare them. And then if you look at the residuals between these two lined up values or positions, you get this plot here. Okay, so there's a bunch of theory that we can show about this. So for example, we can show various results about the Frobenius norm between X hat and X, and we can show results about kind of the maximum distance that X hat I will be from Xi, and we even have a kind of central limit theorem demonstrating that X hat I after appropriate rescaling will be kind of we'll have a normal distribution, technically a mixture of normals, centered around each point, or the true, sorry, I should say the true latent positions. So how would I use kind of this idea of joint embedding, of adjacency spectral embeddings to do joint embeddings, okay? So the idea is that the first idea would be, okay, maybe what we can do is take A bar, right? So take the sample average and embed each of these each of the adjacency matrices to get a and embed the sample average adjacency matrix to get us an embedding. In that case, we will get one embedding that's common to all the graphs, right? Another approach is what we call this omnibus approach. So it's a little bit of a, I think it takes a little bit of thinking to think, okay, why does this work? And some of, a lot of what we're doing is trying to understand, okay, we understand why it works in certain settings, and we're trying to get a better sense of why it works in more general settings as well. And what we're going to do is we're going to take each adjacency matrix and we're going to put that along the diagonal of this large block matrix. So this is an MN by MN matrix. So M is the number of layers. And then on the off diagonals, we're going to put the pairwise averages of the adjacency matrices. Okay. And then we're going to embed A tilde, this large omnibus matrix, using, again, the same idea, the adjacency spectral embedding applied now to this kind of enlarged network structure. And we're going to then get L hat, which will have one row for each node in each graph. Okay, so again, NM by D. And so given those three options, right? And then the third option we're going to look at is just looking at doing separate embeddings, okay? So I'm showing you a plot here just to kind of, again, motivate why we might want to do this. So again, really toy example, but illustrates some of the concepts that we've seen. So if we have, suppose we have two kind of Erdős-Rényi graphs. So one is an Erdős-Rényi P, each edge appears with probability P. And then we have another where the edge probability has been scaled, okay? And what we want to do is these can be thought of as random dot product graphs, where the latent positions are given by basically root p for the first graph and c times root p for the second graph. Sorry, I have squared here, but it should be c. And we want to estimate those latent positions. So we're not going to use the fact that we know it's in an ER. We're going to treat it as if it's a general random dot product graph and see how that works. So when we do that, I'm showing you 3 different methods. The first thing that we might do is embed a bar. The second is ASE is doing separate embeddings. And then the third is using this omnibus approach. And what I'm showing is, as C is on the x-axis, I'm showing C varying for each of the 2, how C varies in graph 2, right? And then on the y-axis, I'm showing you the MSE, the mean square error for estimating these latent positions x1 and x2. And when C equals 1, so that's the case where these are the same graph, basically the same distribution. In that case, the best embedding is the A bar, and then and that's true in both of these networks, right? And then the second best is the omnibus embedding, and the worst in this case is the ASE, right? We're not, and the reason the ASE is the worst here, right, is because we're not using any of the fact that these networks have essentially the same structure, right? On the other hand, if we kind of deviate a little bit, not even that far from C equals 1, the performance for A bar becomes very bad, right? That makes sense, right? Because basically A bar is assuming they're the same, but as we deviate, they are not the same, so we're going to get poor estimates. On the other hand, Omnibus has a much more kind of robust profile, where even as C varies, we're still able to get a good estimate of both x1 and x2. And in fact, it's for most values of C in this plot, it's better than doing separate embeddings. I will note that, if you have, this is sample size dependent. So for very large sample sizes, the separate embeddings would do better. But in this kind of moderate sample size setting, you do see these this robustness where kind of the omnibus embedding provides a good alternative or a good middle ground between separate embeddings and doing embedding A bar. So the theoretical setup that I want to think about is the M-layer GRDPG. So RDPG stands for random dot product graph. The G here stands for generalized, and what we're doing is the generalization here is that we're no longer going to kind of require that that we have these positive semi-definite condition. We're going to allow for negative definite, indefinite expectations and things like that. So the idea of the M-layer GRDPG is that we're going to start again with a set of latent positions X, but then for each layer in the network, we're going to have a matrix B that encodes that is a bilinear form that encodes kind of how the nodes in that particular layer, how their latent positions should relate to kind of either increase or decrease those edge probabilities, right? So BL might encode, different types, might pull from different types of different dimensions of X. So for example, if the dimensions represent different interests, then one BL, maybe in one network, people are, talking about sports. And so you're going to kind of emphasize the dimensions where sports are, that correspond to sports. And then in another network, people are talking about statistics. And so there you're going to emphasize those particular dimensions. And so BL will kind of encode that and encode kind of which aspects of the latent positions are impacting the probabilities of adjacencies in that particular layer. So in this sense, right, then we have that AL given X is again a Bernoulli matrix, but now we're writing it as X BL, and this should be X transpose. So right, all we're doing is we're changing it from having the kind of the identity as the bilinear form to having it as the a generic bilinear form BL. This has been introduced in a few different, or I should say, variations on this this model have been thought about by a few different authors, and so it's definitely it's something that people have been studying for a few years now. So this might at first look like we've kind of limited the space that we're going to look at, but in a lot of ways, if D is allowed to be big, then we can really get whatever we want. And in fact, this model, this M layer GRDPG, is equivalent to if I have separate latent position matrices for each network, XL, then I will, and I allow for these indefinite inner products here. So this is IPQ here denotes an identity matrix or a two block matrix where the upper left block is the identity and the lower right block is the minus the identity with P dimensions for the positive and Q dimensions for the negative. And then again, we're going to have AL given XL now given by the indefinite inner product between the latent positions XL. And you can translate between these two. So if I am starting with kind of the separate latent positions, then I can take X, my matrix up here, as the concatenation of each of the latent positions from each layer to get a kind of big latent position matrix, and then I can encode the BLs appropriately to represent this. On the other hand, I can also write if I start with a matrix X, I can take XL as X times the square root of B, and that will again kind of get me from this top definition to the bottom. So what are we actually estimating when we're looking at this GRDPG model, right? If we are doing the separate embeddings like we've seen, then in that case, right, we're actually estimating the XL. And that, like I said, can be very valuable. And especially if you have, plenty of data, then this might be the way to go. If you're estimating a bar, it turns out that what you're doing, and this is a little bit subtle because it depends on a little bit on whether there's cancellations or not. If it's the case that all the graphs themselves are actually RDPGs, so they're positive semi-definite, then this is then the ASE is estimating the SVD of kind of this big concatenated matrix, okay? And so, so you're kind of look at the estimating or doing embedding a bar will kind of find the common structure among these X's in terms of, kind of their principal, their principal singular values. Note that if it's not PSD, then Bhattacharya and Chatterjee kind of suggest doing something where you look at the sum of AL squared, and that does something very similar. The interpretation in terms of how you're estimating it is a little bit more complicated, but you can do, this does kind of allow you to avoid some cancellations. Still though, right, embedding a bar doesn't distinguish between the layers. So the omnibus embedding basically, again, it's going to provide a biased estimate. So it's going to provide it's not going to exactly estimate the original XLs or something to do, or kind of the SVD of this original X. And it turns out that what it is estimating is if we take kind of the Kronecker product between between an identity matrix and X and look at the SVD of that, right, which has a pretty simple structure, then what's happening is that the omnibus embedding is kind of providing a biased estimate or of the kind of principal singular values of this larger matrix. So it's not going to focus exclusively on the large singular values, but it will kind of, if there is common structure, then most of the emphasis will be on the larger singular values of this matrix. And if there's not, then it will, there will be some kind of bias in mixing. The bias can be complicated. And we can quantify it. Exactly kind of how becomes a little bit difficult, but in a certain setting, we actually can prove a theorem, and it's a little bit, the idea is that basically, if it's the case that the X's arise from the latent positions arise from a distribution F where the second moment matrix here, so the expectation of xi transpose is diagonal, and we also have that the BL, the inner product matrices, those are also diagonal, then in that case, it turns out that kind of the bias itself is also diagonal. So if we look at the difference between kind of the stacked latent positions as represented by L and the estimated latent positions based on the omnibus, then that will have this bias structure where it's kind of multiplicative based on the original latent positions, and these SGs are formed by looking at certain singular values of various kind of omnibus type constructions done on these BGs. Similarly, we can show right, and then there is this remainder term, right? So it's not, so when I'm talking about bias, I'm really talking about an asymptotic bias here, but there is this remainder term that kind of can come into play. And this remainder term we can also characterize, and again, we have this kind of maximum error result, and we also have a similar central limit theorem type result. One of the things that's interesting here is that this covariance structure, there is actually covariance, right? For the original ASE, the asymptotically, there's no, the estimated latent positions are essentially independent. But in this case, right, that still holds for different nodes, but for the same node in different graphs, there will be some covariance, and we can characterize exactly kind of what that covariance structure looks like, to also kind of show how the embedding is kind of pulling out common structure, both in the mean, but also here in the noise, as represented by this covariance. So just to show you what this looks like, these are showing you for 3 different graphs, the rows are graphs, and then the columns are different number of nodes, and it might be a little hard to see on Zoom, but there are these plus symbols here, and these are the locations of the original latent position. So these are each 2-block stochastic block models. Here we have the blocks are kind of are here, and then in this example, there's a little bit of a stronger distinction between the 2 blocks. They're a little bit more separated. And then in the third, just like in the original figure, right, the plot or the graph has no community structure. All of the nodes are originally located just at this point in terms of their latent position. And so basically what we're able to do is characterize exactly how the relationship between this plus and this x, so that which represents kind of the bias term that we are working with, and then we're also able to kind of characterize the structure of these point clouds and understand them as multivariate normal distributions. And actually we can, and as I was mentioning, we can study the covariance among point clouds from different graphs. Okay, so I just want to kind of show you a little example of how we might use this in practice. So I'm looking at two different networks here. These are both networks that are derived from looking at a mouse brain. So there are, I believe, 296 nodes in this network, and in each, and each node corresponds to a region in the brain. And the left-hand side, we constructed a network by basically taking each of the regions and building an adjacency network. So basically, if two regions border each other, if they're next to each other in the brain, then we'll put an edge between them, and if not, then we will there's no edge. Okay, so it's only those that are actually bordering on each other that will have an edge. This second is based off of what's called a DT MRI scan, and this is basically trying to capture the static structure in the brain. So the static, it's looking at white matter connectivity among these different regions. And there's a lot of details that go into kind of how these networks are derived, but essentially what we're doing is we're counting kind of the number of fibers or an estimated number of fibers that are going between each pair of regions here. And what I'm showing you on the right hand, so it's actually a weighted graph in this case because it's based off of these counts. And what I'm showing you on the right hand side is actually just the largest, those edges with the largest weights. And the number of edges on the right hand side is the same as the number of edges on the left hand side. So just keep that. So there is obviously shared structure, but there's also kind of differences between them that we might want to look at. So these are what the two adjacency matrices look like, and I'm actually showing you the weights, the log transform of the weights. It turned out that was kind of the right thing to look at. So I have my kind of ROI adjacency matrix, pretty sparse binary, and then I have my DT adjacency matrix, which is weighted, definitely much less sparse, but has, definitely shares some structure. Here, the different colors are indicating different kind of superstructures in the brain. So these are either forebrain, hindbrain, midbrain, or pure white matter. And I'm showing you the same kind of delineations here with these dashed lines, as well as the delineations between the left hemisphere and the right hemisphere. So the left hemisphere is in the upper left, right in the lower right. So the question we had is kind of how do the neuronal relationships relate to the spatial adjacencies between the ROIs? And are the superstructures meaningful beyond their spatial structure? And what's really cool is if we take a rank 7 approximation of this DT adjacency matrix. So this rank 7 was chosen based off of an automated selection tool for the rank from this paper Zhu and Godzi based on Gaussian mixture models. And you can see that it, this rank 7 is already capturing, kind of, I would say, most of the structure, and possibly doing some denoising, some useful denoising, I should say, to be able to study what's going on in this network. And what I'm showing you here is for each node, for each dimension that I estimated, I'm showing kind of just the nodes ordered according to which superstructure they're in along the horizontal axis, and then the y-axis is the estimated latent position for each of the different dimensions. And you can see that each of the dimensions is in some ways capturing different components of the differences between the superstructures as well as the left and the right hemisphere. So we took a look at this and we noticed that X2 seems to be capturing something to do with the superstructures, right? The hemispheres are essentially lined up with each other, whereas but the superstructures are definitely being separated out. And then in X4, we have kind of the opposite, where the superstructures are largely lined up, and the hemispheres are separated between the left and the right. And so if we actually plot these X2 versus X4, we get this figure. So this is showing where these different or these dimensions of the latent positions end up being. And we were really kind of pleased to see that this is really capturing kind of a lot of that spatial structure, right? This is definitely capturing a lot of what we would expect, the fact that there is common spatial structure. But we also wanted to look at using the omnibus approach. So we took these matrices and constructed the omnibus matrix. I did normalize so that each of the matrices has the same Frobenius norm. That just helps to avoid some of the biases that I was describing earlier. But there will still be, it will still try to capture some of the shared structure. And here, what I'm showing is for each dimension, I'm showing where the estimated latent position was for the spatial network along the x-axis, and for the DT network along the y-axis. And what you can see is that generally the spatial network, from a kind of regression perspective, the spatial network is highly predictive of where the DT network is going to be, right? So it is capturing kind of a lot of common structure. They're not exactly the same, right? There is some variation, particularly in X1, which is representing which you can think of as reflecting a little bit the degree structure. You can see that there is a little bit more variation here, or kind of non-linearity there. And then, also in some of the other ones, there are differences, right? So we're able to see differences between, what is being captured by the spatial structure and what is being captured by the DT structure, and able to use this to kind of look at commonalities as well as kind of find differences. And I know I'm running a little bit low on time, but just to kind of show you how we were able to use this to kind of make some inferences about the impact of these superstructures. We were kind of basically, I just fit linear models of each of these, where I looked at using the spatial structure to predict the DT structure, but then looked at whether I wanted to, or looked at adding in different categorical predictors. So either based on the superstructure, the hemisphere, or all 8 interactions. And basically each dimension is in some ways capturing differences in the spatial structure versus the DT, in either the superstructure primarily or the hemisphere primarily. So the x-axis here is the normalized BIC. So you can basically think of is that larger is better, and so in for example in X6, the green model where I've added in the superstructure categories is a little bit better than the entire kind of superstructure and hemisphere model, and they're much better than those that have spatial only or hemisphere only. This is showing you kind of the residuals of this model and showing how after doing predictions, we can see things like with X6, there is kind of still variation between the different superstructures, even after taking into account the kind of space, or taking into account using this omnibus approach, the spatial structure as encoded by that ROI adjacency. We also kind of did something similar to, or something pretty different, sorry, to verify a similar conclusion. And just to kind of sum up the omnibus theory, when the graphs are IID, we have these, you can easily kind of understand that, again, the omnibus is going to give you unbiased estimates, but then when they're non-identical or non-independent, there is some bias that's introduced, and we can kind of fully characterize that bias in some special cases, and in the general case, there is still some work to do, but I think we can kind of we're getting at some notion of how it's able to capture common structure. And we've also, or some other authors have also looked at correlations among the graphs and how that impacts covariance. And you can also consider more general omnibus constructions where instead of putting pairwise averages on the off diagonal, you might scale those in different ways. And this can be really useful in, say, a time series setting where you want to emphasize commonality among graphs that are nearby each other in time, but not, kind of have that, have the amount of common structure that you're trying to pull out, dissipate as you go further out in time. I have a bunch of references here if people want to, look into some of these different ideas. And overall, thanks. And again, supported by DARPA and MIT Lincoln Labs. And I also just want to thank again my student, Ben Draves, who did a lot of this work. So thank you.
Thank you, Daniel. That's a great talk. So, okay, so please feel free to ask questions in the chat box or raise your hand, and I will try and unmute you. Someone has just asked, can we have access to the slides? I think if you're happy, Daniel, I think we can put these on the web page for the workshop.
Yeah, I can. Yeah, maybe you can just email me and remind me to send you the PDF.
Yeah, sure.
Yeah.
Okay, so so this is all very interesting. It's all quite new to me as well. So I mean, I'm not sure if my questions make sense, but this, I guess, a natural comparison. Well, something that might be natural to compare to would be something like MDS. Okay, which somehow I think this minimizes the strain. But so this is, I think, is relevant for when you only have sort of one graph. I mean, is this something that, I mean, I guess, does my question make sense?
Yeah, right. So MDS is what, so to some extent, the difference between MDS and doing something like this with ASE is really a matter of whether you have dissimilarity scores or similarity scores. So for MDS, right, bigger means that they're more different, whereas in these network setting, we think of kind of bigger as there's more interactions and things like that. But a lot of the ideas from this can also be done with MDS, and actually the original kind of omnibus idea was applied in an MDS setting where we constructed, or my advisor worked on kind of constructing this omnibus and then using kind of some notion of distances between the different modalities to try to come up with a common embedding. Yeah, so that's exactly the right thing to think about if you're more familiar with that.
Okay, I wouldn't say I'm familiar with that. I know the MATLAB function for it. That's as far as it goes.
For those in the audience who know about MDS, yeah.
I guess, of course, so when you're trying to, the purpose of this is to find these sort of underlying latent features which you don't know. Do you have to know the dimension of these features?
Yeah, so, right. So the answer is, yeah, the easiest theory is yes. In the case that these things kind of really come from random dot product graphs, we can show kind of results about consistent estimators and things like that. Generally, we use this method from Zhu and Godzi to do the estimation, but it does really it's not something simple, and it becomes more complicated in the joint embedding setting, where you might have some dimensions that are giving common structure and some dimensions that have differing structure, and so kind of estimating those where there's differing structure using a joint embedding approach will introduce bias, but also just there's not as much signal there, and so you might be kind of suffering more than you're gaining.
Yeah. Heuristically, is it better to use too many dimensions rather than like not enough dimensions? I mean, I guess the idea being is you just subsets of the dimension.
It really, I mean, my statistician's answer is it depends on the inference task. So if you're doing something like prediction or something like that, I would say that's probably the right thing to do. But it really kind of, for other kinds of tasks like hypothesis testing, you might more err towards fewer dimensions or something like that. But yeah, that's right.
Okay, thanks. I don't think there are any more questions in the chat. I don't see anyone's hands up. So I would suggest we go for the go to the break room now, and yes, yeah, and thank you again, Daniel, for a great